Now let us see how we can represent our signals or waveforms in two ways. So we can represent our signals in time domain or in frequency domain. So let us make a table. So first type of signal is the DC signal. Now for the time domain representation of the DC signal, time will be plotted on x-axis and amplitude of the signal should be plotted on the y-axis. That amplitude can be voltage, it can be current, it can be power. Okay. So if it is a DC signal we are going to plot in this way. Now we know DC is having a constant amplitude. Let us consider, for example, if it is a voltage waveform. For example, if it will be having plus 5 volt amplitude or plus 5 volt voltage, it will be plotted in this way. So even if the time is 0 second, after 1 second, after 1 minute, after 2 hours, after 24 hours, what we can say, it is remaining constant at plus 5 volt. Okay. So this same thing, same DC signal, we have to now plot or represent in the frequency domain. Now what is the meaning of frequency domain? Frequency domain means frequency should be plotted on x-axis. So we know the unit of the frequency is hertz. So this will be 0 hertz. After that it will be 10 hertz, then 100 hertz, then 1k, and so on. And amplitude should be plotted on y-axis. Again, amplitude can be voltage or current or power. Okay. Now how much will be the frequency in this DC signal? Now we should know the DC signal, as it is remaining constant over all the time, its frequency is equal to 0 hertz. Okay. Means what we can say, DC signal is available only at 0 hertz and its amplitude is plus 5 volt. So we will be getting only one component of frequency at 0 hertz. So this will be the frequency domain representation of DC signal. So this is our first signal. Let us take our second signal, that is sine wave or sinusoidal wave, which comes under AC signals. Okay. We all know how sine wave looks and we are always representing that sine wave in the time domain. So it is a sinusoidal wave. As it is time domain representation, means time is plotted on x-axis, amplitude, let us consider the voltage is plotted on the y-axis. Okay. And how much is the time period? Now time, as it is a time domain representation, its time period is represented. Okay. Now we know time. What is time period? Time period is nothing but a time required to complete one complete cycle. So let us consider the time period of this signal is 0.01 second. Okay. So understood the time domain representation of the sine wave. Now same sine wave we have to represent in the frequency domain. So again, frequency domain means it is nothing but frequency on x-axis, frequency in hertz, versus amplitude on y-axis. Now frequency axis means frequency should be there, 0 hertz, 10 hertz, 100 hertz, 1k, and so on. Okay. Now as we need to see the frequencies, okay, versus amplitude. Now let us consider its maximum or peak amplitude is again plus 5 volt. Okay. Now we need to find out the frequency of this sine wave so that we can plot the component here. Now how much is the frequency of this sine wave? Frequency we can find out with the help of time period. So frequency is equal to 1 upon t. So if we calculate, it is 1 upon 0.01 second, it will turn out as, I think, 100 hertz. Okay, means frequency of this sine wave is 100 Hertz. So how we can represent the same signal in the frequency domain? So at 100 Hertz, this signal is having the amplitude as plus 5 volt. Maximum amplitude we are plotting. Understood? Or sometimes a spike is plotted in this way at 100 Hertz. So see, same sine wave, its representation is in time domain, its representation in frequency domain. It's that much easy. Next, let us move towards one more signal. Next type of signal is a square wave. Now, we know how we are representing the square wave in the time domain. Time versus, let us take amplitude as a voltage. So, yes, we all know the square wave. But now how to find out its frequencies? Now we must know how this square wave is made up of. Actually, if we are having, if it is given that the square wave is of 1 kilohertz frequency, we can say that if the square wave is of 1 kilohertz frequency. But how it is actually made up of? It is actually made up of with the additions of sine waves, because sine wave is the basic signal, or it is also called as the fundamental signal in the world. So all other signals, square wave, triangular wave, ramp wave, whatever all the signals available in the world are the combinations of sine wave and its another components. So let me first explain how square wave is made up of. So if it is a 1 kilohertz square wave, it is made up of 1 kilohertz fundamental sine wave. So fundamental sine wave. So this is the first component, or fundamental signal it is called as. Then actually in the square wave all the odd harmonics are present. All the odd harmonics of the fundamental sine wave is present. So 1 kilohertz ka odd harmonics is 3 kilohertz. So next sine wave is of 3 kilohertz frequency, not 3 hertz, it is 3 kilohertz frequency, and its amplitude should be smaller than the above frequency. Okay, next odd harmonic of the 1 kilohertz is 5 kilohertz, and again the amplitude is reduced. Now if you go on adding these components, now this is called as what? Fundamental signal or fundamental frequency. Okay, fundamental frequency, and these are called as odd harmonics of this fundamental sine wave. Again, and it will go on continuing. 5 kilohertz, then 7 kilohertz, then 9 kilohertz, and so on. And if you add all these together, we will obtain a square wave. But what will happen? Again, whatever the next 7 kilohertz is there, its amplitude is still again will go on decreasing. So further components, its amplitude will go on reducing. Okay, so how the square wave is made up of is so much important. It is just the combination of or addition of fundamental sine wave with all the odd harmonics of the harmonics is nothing but only just the sine waves, nothing else. But those are called as 1 kilohertz ke harmonics. Now it will be easier for us to draw the frequency domain representation of the square wave. Now how can we draw the frequency domain representation? Frequency in hertz versus voltage. Now we cannot directly draw its frequency response, but we should know which components are present, which frequencies are present in this square wave. So now we have understood which frequencies are present in this square wave. 1 kilohertz, 3 kilohertz, 5 kilohertz, 7 kilohertz, 9 kilohertz and so on with decreasing amplitude. So first fundamental frequency, its amplitude is, let us consider, plus 5 volt. So let me take 0 hertz here. Then if it is 1K, 2 kilohertz, 3 kilohertz, 4K, 5K and so on. Okay. So first 1 kilohertz frequency is available at, first frequency is available at 1 kilohertz. So at 1 kilohertz, how much is the amplitude? Let us consider plus 5 ohm. Next, 2 kilohertz is absent, so it is 0. 3 kilohertz, yes, 3 kilohertz frequency is present, but its amplitude is reduced than the first one. Then 4K is absent, 5K is present, again its amplitude is reduced. Again 6K is absent, 7K is present, its amplitude is decreased. So see, this will be your time domain representation of the square wave, and this is your frequency domain representation of the square wave. So in time domain representation, we are not able to, means suppose we are having some another waveform, any random waveform or triangular wave. So if it is said that this triangular wave is of 2 kilohertz frequency, but we cannot find out ki how many sine waves or how many frequencies are present in this triangular wave, because it is made up of, this triangular wave is again made up of with the combinations of these types of various fundamental sine wave and its harmonics. Now in this case, not only odd harmonics but some another harmonics may be present for the sine wave. So by representing the same signal in this way, we can find out which frequencies are present in the given time domain representation of any signal. Okay.